Okay, I think we can start. There are quite a number of people here already. So Shota will today give his second lecture.
Okay, so let's start the second lecture. So yesterday I was telling how to take the flat space limit starting from the position space correlator. And I introduced the map between the Mandelstam variable and the conformal cross ratio. This is the raw variable that we discussed yesterday. And however, at the end of the lecture, I was also pointing out that this formula one needs to interpret properly, because sometimes even in a simple example of like exchange written diagram in AdS, if you just take the formula and then do what the conjecture says, sometimes you get the right answer. Well, actually, most of the time you get the right answer, but sometimes you don't get a right answer in some kinematical region near the threshold. So now, today, what I'm going to first show is how to derive this, how to understand this failure of the flat space limit in this simple example of the exchange diagram. To analyze it, we use the what's known as the split representation of the bulk-to-bulk propagator in AdS. So let me just first write you the formula for that, which takes this form. Minus mu square r square and times this object. So this is the formula which expresses the bulk-to-bulk propagator in terms of the product of the bulk-to-boundary propagator, where one of them has a dimension d over 2 plus I nu, and the other has a dimension d over 2 minus I nu. And this is a formula, I guess, like some of you are familiar with, but you can just like prove it by, well, you can also like show it by explicit computation. Okay, so now, so this object, so we know that like a dimension of these guys, delta, delta, we need to take it to be large in the flat space limit. And also, we want to take this r to be large because we want to keep the mass of the particle and then send r to large. So naturally, it's also natural to kind of rescale nu so that nu becomes of order r. Then this entire object only contains the very large dimension bulk-to-boundary propagator. So again, like you would expect that you can actually analyze it using the saddle point. And it is true. And then if you take the saddle point value of this integral and then compute it, you indeed get this expected propagator in the flat space times contact diagram. But here, this is actually not the full story. The reason is the following. So the reason is that let's draw the integration contour of the nu. Remember that the nu is related to the conformal dimension by d over 2 plus I nu. So in the terms of delta nu plane, what we are doing is the integral along the real axis, the imaginary axis. So this is like a d over 2 plus I nu. And I said like we want to evaluate this at that saddle point. However, oftentimes if you look for the saddle point, especially for the real z and z bar, Euclidean z and z bar kinematics, oftentimes live somewhere on the real axis. So what you would do, as in the usual case of saddle point analysis, you deform the contour and evaluate it along the steepest descent contour passing through the saddle point. However, there is one subtlety in doing so, which is this pole. Okay? So because of the presence of this pole, sometimes the pole actually sits here. The pole is at the position of like pole is related to coming from the mu square r square. And when this happens, when you deform the contour and then evaluate it along the steepest descent contour, around the saddle point, you also need to pick up the contribution from the pole. And what is this contribution from the pole? And so this contribution from the pole So there are like two interpretations of this contribution from the pole. From the conformal field theory point of view, this contribution from the pole basically fixes this dimension to be something related to nu, and it turns out that this is basically a S-channel conformal block. For operator with dimension delta nu, where delta nu is related to the mass in this way. So the usual formula. And also you can also interpret it from the bulk, and from the bulk it actually corresponds to some kind of like a different saddle point that I drew yesterday, in which actually like the particle mu propagates long distance in AdS. So it doesn't look like something that's locally happening at a point in AdS, so that's why like it doesn't look like a flat space limit. And the problem is that like this contribution sometimes actually over-dominates as compared to this contribution you want to keep. Okay, so this is the reason why it fails. And let me also emphasize that what is the meaning of this part? So as I said, so this unwanted contribution corresponds to the conformal block of operator with dimension delta mu. And what is the other one? The other one it basically corresponds to everything else in this conformal block expansion. So the point here is that this exchange written diagram, this is a kind of probably known fact to many people, but this exchange written diagram is not just given by the conformal block of this operator with dimension delta mu, but it also has a contribution from double trace operator. So basically, this saddle point is kind of like a collective, collectively describe the double trace contribution. So this already tells you that in order to recover the correct flat space propagator, what you need to do is to throw away the conformal block of operator with dimension delta mu, and then just keep the double trace part. So this might be slightly counterintuitive because, like, as you can see, that this propagator is really the propagator which has a pole at the position of like a particle mass mu. And so you might think that this actually corresponds more to the conformal block of the particle delta mu, but it's actually not the case. And the fact that you exchange this particle has some imprint also in the double trace, and then that's precisely the part that we want to keep. And we want to throw away the direct conformal block part. Okay? So this is like what this perturbative analysis tells you.
Should I ask?
So I wanted to ask, in this Mellin approach, usually I thought if we take the Mellin diagram, it has only the single trace pole, and this is a single trace pole that survives in the flat space limit. So it looks very different there, right?
Right. So that's true. But like I think you never. So if you want to get the flat space answer, yeah. Okay. Yeah, that's true. It's different. Yeah. Yeah.
There's a direct connection from Mellin space to position space just by doing the inverse Mellin transform. And there, the Mellin variables, when you do the contour integral, you need to pick up some poles. And the poles you pick up exactly come from the Mellin poles, which correspond to this single trace block. So these poles from the Mellin amplitude also give the same divergence region. So in this technical level, they are exactly the same. But if you don't integrate Mellin amplitude, just take the flat space limit of Mellin amplitude itself, you get just the amplitude, yeah. But for that, you need to first make sure the Mellin amplitude itself is well-defined in the first place, and that's less justified than the position space correlator.
Manuel.
I was wondering what is the connection to geodesic Witten diagrams, because here you're doing a saddle point analysis on the integral over nu, but you're not touching the bulk integrals, right?
Right, but yes, we are not touching the bulk integral, but like in the end, we are interested in the regime in which mu is also large. So in the end, like everything becomes geodesic. So this is a kind of like well, as you know, like a geodesic Witten diagram is a conformal block, but you also need to further saddle point approximate that integral, and then the entire thing becomes saddle point, like the geodesics.
So out of the things you discussed now, it's not the pole, but the other term that becomes geodesic. I see.
Can I ask one more question?
Yep.
Can I understand all of this from a differential equation that the Witten diagram you're considering satisfies? Like you have two solutions because it's second order.
Okay, that's a good question. Probably yes. It's so this is typically like the flat space limit exponentially suppressed or exponentially enhanced contribution depending on the kinematics. So if you solve the differential equation, keeping track of this like a radius r, and then do some kind of WKB analysis, maybe this is a kind of like a exponentially suppressed contribution in the WKB analysis. Okay, so so far I've been telling you that just like doing the perturbation theory. So now let's do something more serious. But this part becomes gets quickly very technical. So I will not go into the technical detail, and then just summarizes what people have done. So far I was telling you that there is a subtlety. So the question is how to avoid this subtlety, and also like beyond this perturbative Witten diagram analysis, how to identify the problem, and then how to make sure that the limit exists. And this was discussed by, in the case of 1+1 dimension, by Ife and Miguel Paulos and then Lucia. And in the case of like higher dimensions, it was discussed by Shan and Balt sitting there. And the idea is, so in order to really establish that it has a finite limit with appropriate prescription, it turned out that it's more useful to expand this conformal block, sorry, the 4-point function in terms of what's called Polyakov-Regev block. So what is Polyakov-Regev block? So this is basically something like a ST channel symmetric version. Conformal block. And you can also describe it as some kind of like a sum of Witten, ST Witten diagram plus contact terms. And and alternatively, this expression actually arises from the conformal dispersion relation Simon and Dean worked out. So there is a kind of like analog with the dispersion relation for the. That's a good question. Does anyone know? Yeah.
The Polyakov block, as was introduced a little earlier, is supposed to be fully crossing symmetric. This is only ST crossing symmetric. And it's the thing that naturally comes from a dispersion relation where you have to pick a channel to do the contour integral. And it's Regev because it has good Regev. By suitably fine-tuning the contact terms, it has good Regev behavior.
So the dispersion relation basically allows you to write the full 4-point function in terms of what's called the double discontinuity of the 4-point function. And here you need to pick a channel, as Leonardo was describing, and discontinuity of the 4-point function. So if you write the write the discontinuity of 4-point function, you can recover the full 4-point function. But the Polyakov-Regev block basically comes from the taking the d-disk of the conformal block. So combining the dispersion relation and the usual conformal block expansion, you arrive at, you can establish the existence of this kind of expansion.
block expansion?
Yes.
Is it known that it converges? Is it known that this is a convergent expansion?
Yes.
How do you know this? What's the proof?
Well, because you start from the rigorous story, and then, we have a very long paper where we explain this.
But the problem is that this equation that is written is not a rigorous equation. It's double discontinuity dispersion relation. It's not proven in full generality. It requires some.
So where's Dalimil?
Rigorous is this the issue of the light cone limit on the second sheet. So if you can prove that the light cone limit on the second sheet is asymptotically dominated by identity plus something that is suppressed, then the twice subtracted dispersion relation is rigorously established, and then by plugging in the conformal block expansion into it, you would derive this expansion into Polyakov rigid blocks.
Yeah, and it's important to emphasize that the coefficients here are precisely the standard OP coefficients. So this is the same as the standard conformal block expansion, but we're replacing the conformal blocks with these ST crossing symmetric blocks. Those are the usual OP coefficients.
But this doesn't tell anything about whether this equation is convergent or not.
As Dalimil said, under some very mild technical assumption, you can just prove this equation.
I disagree that that assumption is a very mild technical assumption, because that assumption about OP on the second sheet, it goes beyond the Bootstrap axioms. And in fact, it's one of the big open problems in my field, that there are so many results which are built based on that assumption, and it's not sufficiently often emphasized that we don't know if those results apply to every CFT or just a subclass of CFTs.
Okay.
Okay, so thank you for clarifying discussions. And okay, so I guess what I'm going to tell you is even less established, but okay, so let me just say the procedure Bolt and Chan described. So the procedure Bolt and Chan describes is that now, if you just take this and then take the limit, of course, we are going to end up with the same problem. Now, the idea is to define some subtracted 4-point function. The definition being, you also take the Polyakov rigid block. So the use of the Polyakov rigid block is more about really establishing some features, some properties, or proving some properties that we want to establish, and then subtract the operator whose dimension is below the threshold. So I said yesterday that the operators above this two-particle threshold doesn't have a bad region on the first sheet. So what we need to care about is the operator below the threshold, and then we basically subtract the conformal block in the S channel plus T channel. Okay, so this is a object that they defined, and then under certain assumption, which I'm going to tell you, they basically argue that this becomes a dispersive representation T of the amplitude, which is basically a usual dispersion relation expression of the scattering amplitude.
So sometimes, most of the time, there would be different operators in the S channel and the T channel. Mm-hmm. So these O primes are in the S channel or in the T channel?
Okay, that's a good point. I guess so far the result has been established for the identical operator.
Okay.
Yeah, I should have emphasized this. Okay. So
Shota, a quick question. So in the flat space, there is also crossing symmetric dispersion relation. Is there a CFT uplift of this?
Yeah, I guess that's a very good question, and then that's probably one of the open, the future direction, like whether there is a use for crossing symmetric dispersion relation for the CFT, and whether one can use it to say something about the flat space limit.
Since we are at it, I just understand what you guys think about this Polyakov-Regge block expansion. So for the usual conformal block expansion, even that expansion, I mean, doesn't converge everywhere, right? And if you're in the Euclidean, it converges in a certain domain. You know, nobody would claim that it converges outside of that domain. So this expansion, do people understand, I mean, based on these arguments, which are plausible but not fully rigorous, in which domain it's supposed to converge? What is the rate of convergence? Is it exponential as for the usual conformal block expansion, or is it slower than that? And has anyone tested this numerically by just taking the known OP coefficients of the 3D easing model, plugging it, and see if it does converge or not?
Yeah, so if you forget about this issue of the light column on the second sheet, then this is rigorously established, and this expansion converges in the intersection of the convergence region of the S and T channel OPE. So basically two complex dimensional plane in parameters by Z and Z bar as independent complex variables, minus the S and T channel branch cut. And it converges everywhere like some power law. It has been checked in, I guess you can check it in the free field. We checked it in the Ising model as well, as far as I remember. I don't know if...
And what controls the power law exponent with which it converges?
It's essentially the number of subtractions. So I think the power law exponent. Yeah, so if you restrict to the twice separated dispersion relation, this is going to fix the exponent. I don't exactly remember what it is, but maybe it's like 1 over delta squared or 1 over delta to the 4, something like that.
Pretty spectacular.
Yes. I didn't make the plot, but I think it's spectacular.
Converges with that. Okay, guys, I mean, I'm happy that you are comfortable with this formula. Yeah. I mean, in our field, we like to be watertight. We like to claim that we are more rigorous than other areas of theoretical physics. So.
There's numerical checks, including the Ising model.
No, I'm just saying that, since everything indeed points in the direction that it does converge, you have all these checks, why not just close this last loophole and show that the OP on the second sheet does indeed. I mean, it's still an important question to clarify. I mean, mathematicians, they like to, if you have a system of axioms, you would like to verify which axioms are independent of other axioms. So is this OP on the second sheet, is this like the axiom of choice in mathematics, or is it, or does it, which you may accept or reject?
I don't know.
Yeah,
one logical possibility, of course, there is a certain class of CFTs that include all CFTs we care about.
Yeah.
In fact, the property of the light cone limit on the second sheet, which is needed to establish this twice separated dispersion relation, is extremely mild. So essentially, the only thing that you need is that if you subtract identity, then the rest is the light cone limit of this difference goes to zero. So that it's dominated by identity. Everything else is subleading. You don't even need the other low twist operators. Extremely mild property of the light cone on the second sheet, and then everything is okay.
But please continue. I was just like, I wanted to save time. Okay, so Yeah, but I agree that it's important to establish like more rigorously, because like if we want to use this like a flat space limit of AdS approach as a kind of alternative of like an old LSD approach to the scattering amplitudes, which like many people like studied in the past in the 60s, 70s, of course we first need to establish like the properties on the CFT side very rigorously, so that one day we can beat those LSD approaches. Okay. With that said, let's go back. So this is what Shannon Bolt has kind of established or says under certain assumption. But this basically first involves two claims. First of all, this actually involves the claim that this limit is actually finite, because we saw in the perturbative example, if you don't do something like this, like you get infinity. And so one thing they proved is that the limit is finite under certain assumption. The certain assumption is they made is that they first assumed that the limit is finite in some subregion in the Euclidean kinematics. So this is a kind of unphysical kinematics from the scattering amplitudes point of view. Sorry. And so they first assume that this limit is, that object is finite when R is infinity in this domain. And then once using that as assumption, they could prove that you can actually, the TST that you get is finite. For fixed U. In the entire complex S-plane on the first sheet. Okay? So well, very roughly speaking, so this is a kind of like a purely Euclidean kinematics, and if you go away from it, like these operator product, these Polyakov-Regge expansion or conformal block expansion oftentimes acquires additional phase, and that typically improves the convergence rather than destroy the convergence. So it was kind of enough to assume that this converges in this Euclidean domain, and then assuming that they could prove that it converges in the entire S-plane except the cuts. And so using this, another thing they could actually establish was they could rederive first our Martin bound about high energy behavior of the amplitudes. So this is more, yeah, I don't have time to explain what that is. So like this is more like a comment for those who know this. And another thing they could establish was, important thing is that extended nonlinear unitarity. So if you don't know what extended means, you can just like drop this, and then what they showed is the nonlinear unitarity. But if you know what the extended means, which basically deal with the situation in which like the branch cut node doesn't start directly from the 2 particles threshold. So this is relevant for like there is in the case there are particles which are smaller than the external mass, and in that case like people studying amplitudes in the old days kind of like a conjecture that there is a kind of extended unitarity region which is called extended unitarity, and then they could also prove it. Well, so maybe extended and a nonlinear unitarity. So those are kind of things like they could establish using this analysis. And sorry, Shan and Baud for 3+1 dimensions, and then Lucia, Ife, and Miguel Palos for 1+1 dimension. Okay, so I don't have so this really explaining like how they derived the nonlinear unitarity in detail is a little bit too technical. So I'm going to just like give you some a schematic and or pictorial understanding how CFT knows about nonlinear unitarity, which is like SS, roughly speaking, SS dagger smaller than 1, which is nonlinear, and how that arises from the usual CFT unitarity, which is saying that like OP coefficients square are positive.
So Shota, before you go, can maybe ask about Shan. So what is the intuition or what is the status of this assumption that there is this domain and the limit exists there? It seems very abstract.
Yeah, so of course, ideally you don't want any assumptions. You just want to say, let there be a connected 4-point function of CFT that obeys the CFT axioms that Slava mentioned, and take the large delta limit and show that it becomes a consistent scattering amplitude. That's the dream, and I'm not even sure it's that hard to prove. So this was not something we were able to do. So we had to make some assumptions. And so 2 assumptions. One is like the existence, the melt behavior in the light cone limit on the second sheet, which is necessary for this dispersion relation. It would be great to prove that because we really need it. So I want to say the same thing as what Slava said. We can be rigorous here because we have well-defined axioms. It would be great to dot all the I's and cross all the T's and have mathematically rigorous proof. And then here's the second assumption, that it's finite in some domain. It's probably sufficient to make it so to say that the limit exists and is finite in this domain is of course a pretty strong assumption, and it would be, we can probably weaken it to say that the limit should only exist and be finite at a few points. And then because you have a dispersion relation, you can show that therefore the limit exists and is analytic in the entire S-plane, because the discontinuity cannot blow up because it's finite at a few points. And then you can from that show analyticity. The proof is very simple from that. But it would be great to show that connected correlators cannot become arbitrarily big, and therefore this limit is finite. So that's another thing that is on my to-do list, or should be on more people's to-do list. It would be great to prove that in the large delta limit, connected correlators cannot become too big at a few points in this domain, which we call that Shota explained this relation between ST and U and Z and Z bar. So this is just Z bar somewhere in some subset of the Euclidean region. So Z equals 1/2 is one thing, or Z equals 1/2 plus I square root 3 or so, that other symmetric point. Like, what's the bound on the connected correlator in that limit? Can we prove it analytically? That would be very nice. We're currently doing some numerics just to see if a bound like that could exist. But the numerics is inconclusive at the moment. But it would be great if someone has an analytic proof.
Yeah, I guess like we also probably have to say in 1+1 dimension, this is like they don't actually need this assumption. Like you just need to make some assumption on the spectrum of the operator so that anomalous threshold doesn't show up.
Yeah, this is, so we had a further assumption that the first operator is at square root 2 delta, which means that there are no bound state poles in the region S less than 2.
There was, say, only 1 or 2 or some finite number of points where there's a pole. Is it easy to improve the proof to take an account of those?
Yeah, that is actually, that would probably be easy. Isolated bound states in that region is fine. Anomalous thresholds, which extend in that domain, that seems harder.
Okay. Thank you.
Okay. Yes.
Setup, are there any assumption referring to information for QFT in AdS? Because suppose we have 2 different QFT which has the same mass gap, then you take a flat space limit. How do we distinguish between this amplitude for two different series. You may have different limit, and how do you make sure the limit exists?
So you're thinking about like the same spectrum, but the theory is actually different.
Yeah, because seems to me here it's purely a CFT setup. So
Right.
how do you separate different massive series in AdS?
Do you want? Okay, sure.
Yeah, so the mathematical result is then, so let me rephrase your question. What if you have two QFTs in AdS?
Yes.
And for every value of R, you take a sequence for all the integer values of R, but for the even integers, I take one theory, and for the odd integers, I take the other theory, and therefore, like the limit of this sequence does not exist because I oscillate between two amplitudes. Right, that's one example of the problem that I think you're formulating.
But so do you mean you need to assume the existence of the limit? Then you say something.
Well, here we did, yes. I think more generally, if you want to exclude that scenario, you can say, right, for every sequence there exists a convergent subsequence or a subsequence that converges. This is sort of a standard mathematical trick to avoid that.
Okay, thank you both for answering the question. So now I'm going to present you like some schematic picture about how to understand the nonlinear unitarity arising from CFT. So for that, let's go back to we are just talking about CFT, and then let's imagine considering the hemisphere, in D-dimensional hemisphere, and then you put some local operator here, O1 and O2. And then that creates some state on this equator of the hemisphere, and then let's call it psi. And now take this psi and then let them time evolve using radial quantization Hamiltonian, which is the rotation operator, and then do it by pi over 2 times psi. And then divide by square root, the norm of the psi, which is in CFT language, basically corresponds to the sphere 4-point function. So let's just introduce this object. And as pictorially, this basically corresponds to you construct this state. And then here you have a state living on the equator, which is SD minus 1. And then you are doing the time evolution using the radial quantization Hamiltonian by pi over 2. So this is basically the state you get. And similarly, let's introduce out state. And what we do is the same, but we just put plus id pi over 2 psi, and then we again divide by the norm. Okay. And so now what I'm going to do is to consider these two kind of states, and then, well, maybe I should write it here, and then compute the matrix of norms, overlaps. So you have like an in state and out state as a row and a column, and then compute the matrix element of overlap. So here sits in and in. So this is just 1 because like this e to minus I pi d over 2 cancels out if you take a Hermitian conjugate. And then in the end, you just get the sphere divided by sphere. So this is 1. Whereas like out and in is non-zero. So and it corresponds to something like this. So you have 2 operator here, 2 operator here, and then separated by pi. Okay? And then in and out is basically the same with minus pi. And here sits out and out, which is also 1. Okay? And then I'm going to call this object, which is just some kinematical limit of the 4-point function, as some kind of S matrix. And then I denote this, and then like if I denote this by S, and then this should be S dagger because it's a complex conjugate. And the important point is that this matrix element is just like matrices of norms or overlaps. So this, in the unitary CFT, this has to be a positive matrix. So this has to be the positive matrix. Okay, and from this, it automatically follows. So, and then this positivity comes from the unitarity of the underlying CFT. And from this, it automatically follows that this has a determinant which is positive. And that is basically S1 minus SS stagger must be positive, which is precisely the condition that one wanted to establish. Of course, in practice, in higher dimension, we need to, in order to really write the nonlinear unitarity, you need to project to some partial wave sectors. But you can also do it here as well, but I just didn't explain it because it's going to take a while to explain the detail. But you can basically do the same by putting some projection operator to some spin sector. So here, as you can see, that actually, I was not even imposing, considering the R going to infinity limit. So this is some particular property of this matrix of the correlator, which is always true in CFT. But the point here is that this object in the large R limit becomes the flat space amplitude. That's a very good question, and then that's indeed that's actually an open question. Yes. So the open question here is, of course, the unitarity is not SS dagger smaller than 1. SS dagger equal 1 is the full unitarity of the amplitudes. So the question here is that can we show that if you have a complete basis of states, can we show that SS dagger equal 1? One thing I can say is that imagine you have a bunch of in state and a bunch of out state. And then if you include a lot of states, then after a certain point, this matrix G starts having 0 eigenvalue because rows and columns become non-independent, right? If that happens, determinant of G must be equal 0, and then that roughly corresponds to 1 minus SS dagger equals 0. That basically means that to put it another way, that is related to a question of whether we can span the entire Hilbert space of CFT by multi-particle operator insertion of some light operator, which is below threshold. Because this is how we construct the Hilbert space of the flat space. You just introduce a stable particle and then allow yourself to have a multi-particle states. So the question is related to this is whether this gives you the complete basis of state. This is rather a non-trivial question because this is not how we span the complete basis of states in CFT. In the CFT, the complete basis is given by inserting a single operator but allowing various different operators. And it's highly non-trivial that this kind of basis becomes also normal state. First of all, you might say that this might be overcomplete, but if it's overcomplete, then the unitarity equation needs to be modified. So there is a sense in which this kind of states gives you the also normal state, at least in the large R limit. And establishing that is a little non-trivial question. And in fact, there is some subtlety even in simple toy model cases in which between this basis and then this basis. And then that's actually sometimes leads to some kind of a modification of the crossing symmetry, which I hope to talk about. I'm actually not sure if I will be able to talk about, but which I'm hoping to talk about tomorrow.
So just to make sure, what is the subtlety here? So it's clear that it's pretty clear that by inserting these light operators, you can span the whole
Right.
Hilbert space. You're saying that it's not clear how to construct an orthonormal basis from these things?
Right. So yeah. So in which sense? Maybe in which the question is in which sense? How to yeah. How, I guess I agree. Yeah. So that how to construct orthonormal. How this becomes orthonormal basis. That's probably the proper way to state the problem.
Okay.
Okay. So far, so good. So now I'm moving on to the second lecture. Actually, when did I start? 10:20. So I spent. I have half an hour, slightly less. Okay. Right. So I have until 35. I have until 35, right? Yeah. Okay. All right. Yes. So now I'm going to move on to the next topic of my lecture. Which is about confinement and mass gap in AdS. I already mentioned 2 papers. Like in the beginning, I mentioned my paper with Lorenzo and Christian and Zimin last year, and also mentioned like the paper which appeared yesterday by Ricardo and then Lorenzo, Fabiana, and Marco Cerrone. And I also need to mention that there is an important paper which discussed, kind of initiated the discussion on this topic by Aharoni, Barkutz, and Tong, and Yankilovich. All right, so now the question I'm addressing is slightly different. So the question is, can we use AdS CFT, AdS as IR regulator? And as I explained like yesterday, that because of this, like you can actually, there is a hope that you can understand something about confinement and the mass gap in the semi-classical regime. And then can we learn something about mass gap and confinement? So this is now the topic that I want to talk about now. Okay? So let's set the stage. So I'm going to talk about YAM-MILs in AdS and then different boundary condition. So the theory that I'm going to talk about today is YAM-MILs in 4 dimension. So it's like YAM-MILs in AdS4. So the Lagrangian is basically this one, the usual YAM-MILs action, but on a curved manifold. Maybe I need one quarter here. And if you solve this equation, if you solve the equation of motion of the free series, solution to the free equation of motion, so this is a kind of standard exercise when you do the AdS CFT in the presence of gauge field, and then expand the solution near the boundary. I hope you understand what I mean by Z. Z is just like a radial coordinate which always shows up in AdS CFT. Then there are 2 asymptotic behavior which are allowed. By the equation of motion, and one becomes finite and a constant at infinity, whereas at the boundary, whereas the other one decays at infinity at z equals 0. And then generally we need to set the boundary condition so that like AdS isometry is preserved and the variation problem is well defined. So And then it turns out like there are two natural boundary conditions, preserving AdS isometry. Well-defined variation problem. So this is kind of like a very similar to analyzing the boundary condition of the free scalar field. Well-defined variation. And as in the case of free scalar field, you have two different ones. One you would call Dirichlet boundary condition, and the other which you would call Neumann boundary condition. So the Dirichlet one basically corresponds to setting this AIX to be 0. So the only remaining kind of operator that you have afterwards is this one. Probably I should, so these indices are super confusing, so I just write J mu, sorry, and then A mu. Right, that's true, yeah, so I should write, yeah. Yeah, I should write I indeed, yeah. So mu runs from, yeah. Sorry? A sub z is 0, yes, yeah. Right. And well, I'm gonna, right. And then the other one is imposing this other one to be 0, then you are left with this object. And a little bit more, so as Sylvie pointed out, like this is in the gauge where A sub z is 0, but a little bit different way of phrasing it is that Dirichlet boundary condition corresponds to setting Fij equals 0, where Fij is a field strength, and whereas the Neumann boundary condition corresponds to setting Fiz equals 0. Where I and j are basically the direction perpendicular to the, also direction along the boundary, whereas the z is a radial coordinate. So what is the physical meaning of these two boundary conditions? Let me just first point out that it is actually the Dirichlet one, which you are probably familiar with in the context of AdS CFT. So if you choose the Dirichlet one, so the Dirichlet boundary condition leads to the familiar statement that if you have a gauge field in the bulk, then on the boundary you have a global symmetry. So if you choose the Dirichlet one, you have a 3D conformal theory with SUN global symmetry. Okay? Whereas if you choose Neumann one, because this AI plays a role of the gauge field, actually the gauge field survives at the boundary. So you get some 3D conformal theory again, but with SUN gauge symmetry. So you have a gauge field on the boundary. Okay? And both of them are very interesting because Neumann one, because you have a gauge field on the boundary, if you choose a Neumann one, even if the AdS size is very small, all the operators that are physical are actually gauge singlet. So this leads to kind of like a perturbative confinement that I mentioned yesterday. So the color degrees are confined, even in the regime perturbation is trustworthy. However, today I'm going to focus more on the Dirichlet one. So let's talk about what we expect in the Dirichlet boundary condition. Okay? Right, but here, like so okay, probably the best thing I can say is that if you go to the small AdS in which perturbation is trustworthy, there is, for example, an operator corresponding to trace f mean Fij, Fij. And the dimension of that operator follows from the just the usual counting, assuming that there is a gauge field on the boundary. And so let's talk about the Dirichlet one. And oh, so okay, that's a good point. Okay, so perturbative confinement is a little bit confusing because like, normally we cannot talk about confinement using perturbation theory. But here, AdS is kind of, in some sense, better because, like as you already said, like a confinement and a deconfinement or Higgs phases are distinguished by the like a area law or perimeter laws of the Wilson loop. So AdS has a weird feature that area laws and perimeter laws are basically the same, because if you in AdS, because like especially if you put the Wilson loop near the boundary, because the because the metric takes this form, you cannot really distinguish area laws or the perimeter laws. Kind of, it's always like a dominated. Well, it's always like a proportional to area. Sorry, what's the best way? It's always, okay, it basically gives the same behavior. And to directly answer your question, you don't see the linear potential directly here because of the AdS curvature. Like it's very contaminated by the AdS curvature. So here I'm distinguishing confining phase or deconfining phase by looking at whether you see a color singlet degrees of freedom, a color non-singlet degrees of freedom or not. So in the deconfined phase, you can basically scatter quarks or like a gluons, but in confined phase, you cannot. While the asymptotic states are like a glue balls or a color singlet object. Here, I said perturbative confinement because the operator that exists in this theory are all color singlet, because you have a gauge symmetry already on the boundary. But I agree, like it would be nice to have a better definition, like a sharper definition of a confinement.
So that was exactly my question. So the statement is that on the boundary CFT, there's only SUN singlet operators. Is there anything beyond that when you say SUN gauge symmetry? I mean, we only know that there are singlets, but do we?
Yeah, that's true. So like I can say something more in the perturbative regime, but beyond, like if you're away from the perturbative regime, it's hard to kind of like pinpoint what that theory is.
But even in the you can say in the bulk, but in the set of local operators in the CFT, you just see singlets. How? I mean, what is the meaning of the statement that there's an SUN gauge symmetry on the CFT? I don't understand. What does that mean?
Well, yeah. Okay, I agree. But I'm just saying that like you can list the operator, but maybe that this is more, you would say this is more like a bulk logic. But you can explicitly list the operator, assuming that you have some gauge field on the boundary.
But the gauge field is a dynamical field, right?
Right, yeah. Okay. For probably U1 that works. I'm not sure if do you think that works or for no abelian theory? Mm-hmm. Yeah. Okay, yeah, you can say that as well. Yes.
By just gauging the global SUN symmetry.
That's also true, yeah. Okay. Right. So let's now focus on Dirichlet case. And so what kind of operator do we expect to get in the Dirichlet boundary recognition? Well, first of all, like as I said, like we have a 3D conformal theory with global SUN symmetry, and we do have this operator, which turned out to be the conserved current of the SUN global symmetry. So there is an operator with dimension 2. So the dimension is 2 because like a boundary dimension is 3. We are talking about CFT3, AdS 4. So the conserved current has a dimension 2. And this should have exactly dimension 2 because of the conservation law. So this is what we expect to happen, at least in the small AdS radius. On the other hand, we don't expect to see this kind of operator in the flat space limit because first of all, in the flat space limit, we believe that the Yang-Mills theory has a mass gap. So all the operator should have very large dimension, which goes like M gap times R in the near flat space limit. So here, clearly, something has to happen in the middle region. And we somehow, like this is basically telling you that this Dirichlet boundary condition becomes unstable at certain critical radius. Okay? So now the question is, so what is the mechanism for instability? And then there are several scenarios proposed by this paper by Harney and others. And and we also kind of like proposed yet another scenario, which we thought like a more plausible in the paper last year with Christian and others. So I'm going to explain to you what are those scenarios in the remaining 10 minutes. So the first scenario discussed by Aharon and others is basically Higgsing. So this leads to some continuous phase transition. And basically, the picture is the following. So let's draw the same one. So we have like a dimension 2 operator here, and which is a current, J. And the expectation, so the scenario they proposed is that probably there is some operator, scalar operator, which are in the scalar operator in the adjoint representation of SUN, hits the marginality at some point. So this is dimension 3 is a marginal operator. So it starts out as an irrelevant operator, and then as you change the radius, somehow there is some operator whose dimension goes down and it hits the marginality. And then they conjecture that if this happens, you can have this famous multiplet recombination. So this operator or adjoint can show up in the conservation law, and then together they become long multiplet. And then afterwards, like you don't have any more conservation law, and then dimension of this operator starts going up. So this is the first scenario they proposed about how to lose the conserved current as you increase the AdS radius. And the best candidate for this operator is basically Ji. So you just like consider like a product of two current, so that like it becomes scalar, and then project to the adjoint representation. And right. So this looks nice. Like it's also kind of something that we are familiar with in QFT, like a multiplet recombination and so on. But at the same time, this has a disadvantage, like already discussed in the paper by Harani, that it seems like if this is true, and then like if these all operators, if these operators like a JI or like a multi-trace of JIs all survives as a massive particle in the flat space limit, it seems like it has like a number of states maybe too many. Of course, like, this is not a very strong argument, but intuitively, this sounds like leading to too many operators or too many states in the flat space limit. Too many means that, so for each JI, basically like the number of JI is the same as the number of JIs in the conserved current. So basically, you have as many massive states as the number of gluons, like the degrees of freedom that you had in the deconfined phase. It's just that they all become massive. That sounds like a too many number of states in the confining phase.
Like too many glue balls would be degenerate, or what's...
Right, too many glue balls.
Okay. So I have a... Maybe you can clarify. So here you would remain, so the non-singlet states of SUN would just start to become more heavy, but they would still stay at finite energy.
Mm-hmm.
So what's the expected behavior when you go to large AdS for a non-singlet state in the...
Yeah, okay. So, right. So you can... That's a good point, and you cannot like just discard this scenario just by saying that this sounds like leading to too many massive states, because there is a possibility that those non-singlet operator has a much higher growth of the dimension, and they just decouple in the flat space limit, and what are left in the flat space limit are just singlet states. But I think like what they said is like it's a bit hard to come up with such a. It's just harder to imagine that such a fine-tuning happens.
But what is the picture like when you go to large AdS and you have a non-singlet in the middle? There will be like a flux tube to the boundary or something, and and then it would come from like the tension of that flux tube. Can we ask?
Yeah. Okay, but
is the expectation that the non-singlets remain all the way to infinite R? They just scale faster with R, their dimension, or they should disappear at some critical R?
I think in this scenario, probably it's more natural to imagine that it kind of becomes infinitely heavy and you won't see it. But in any case, like the recent paper by Lorenzo and then Fabiana and then Ricardo and then Marco Cerrone, basically like their result actually disfavors this scenario. So I don't want to talk much more about this scenario. Yes, exactly. Like they computed the anomalous dimension of this guy, and it actually goes up rather than going down. And the second scenario is decoupling. So this also leads to some continuous transition. And in the decoupling scenario, so like if you have a conserved currents, a natural object that you can study in the two-point function is like this Cj, which is a normalization of the two-point function. And in this scenario, they discussed the possibility that maybe this Cj, as you increase the AdS radius, goes to 0 at some point. And when it goes to 0, basically these currents decouple from other operators. Okay? And well, because it kind of becomes a null state. So this is the scenario they discussed, and I would say like this is plausible. It sounds like plausible. Because maybe when this happens, like you also lose all the non-singlet operator, they just decouple or it becomes null state and disappear. But on the other hand, it's a bit mysterious what happens after the post-decoupling phase or boundary condition is a bit mysterious.
Actually, is there any quantitative theory that can be developed near this decoupling point, or in the first scenario near the point where this operator, a joint operator? Are there any examples of when this happens in strongly or weakly interacting CFTs?
Destroys the weak.
Because I mean the multiplicity combination, we know it when it happens around free theories, but is there any example of a family of strongly interacting CFTs where this scenario is realized?
Yeah, indeed, that's a good question. Like I think all the examples we know are around the free point. Indeed.
Yeah.
And it's also related to the fact that this is kind of like a boundary dual of the Higgs mechanism. So is there maybe like the bulk counterpart of the question is whether there's a strongly coupled Higgs mechanism, maybe?
Also, like what is, I mean, the fact that this operator or joint is present, okay, it definitely creates the possibility for decoupling, but is there any quantitative theory that one can develop which would say how this decoupling would actually be driven and, you know, what's... Both, sorry, both. Like, okay, I don't know any calculation that one could do apart from the fact, say in the first scenario, that, well, this operator is there, so it can happen, but why would exactly it happen?
I see, but I guess like there are something that we can learn right after this Higgsing, probably, because like I think like Sasha studied this higher spin, slightly broken higher spin symmetry. In that case, like well, the analysis is purely in terms of operator, like a CFD language. So probably one can do some CFD analysis and how the different anomalous dimension like depends on this small parameter. Okay. So this I can imagine doing. And here, I don't know. I don't have a clear proposal. Okay, so in the remaining 1 minute. So there is a third one.
Sorry, Shota, a very quick question. So if we take a 4-point function of currents in a CFT, isn't the bootstrap bound lower bound on J given fixed CT?
Yeah, that's true. Yeah,
but you don't have CT, maybe.
Yeah, we don't have CT. Yeah, we don't have CT, but like I guess like that's a kind of interesting future direction, like to try to distinguish these different scenarios using the bootstrap. So that's why I'm talking about this in this workshop. So tachyon. So the third one is called tachyon, which is discussed in the paper by Harani. So what they say is that maybe some scalar operator hits the BF bound delta equal 3/2 at some critical value. So there is a sum operator, and then whose dimension hits this bound. So this is like this BF bound is known as like basically in AdS you can have slightly like a negative mass squared, but below, okay, let me just draw the usual one, like you write the mass square and then dimension. And the relation between mass square and then dimension is like this, like a delta minus d. And in this case, d is 3. Then the relation goes like this, and here you have 3, and then here you have 3/2. So until here, does not lead to tachyonic instability. But if you have a particle below here, then there is a tachyonic instability. And then, because of this, if this hits and then it goes below, maybe there might be some tachyonic instability. So this is something that you often learn when you first learn AdS CFT. There is this BF bound, and you cannot go below that. So the plus is this is what you learn in AdS CFT. But on the other hand, it's a bit unclear whether this BF bound has any a significant meaning in the non-perturbative interacting theory, because delta equals 3/2 is from a CFT point of view just nothing special, just some random number, and importantly, the way people derive the BF bound is basically analyzing the Klein-Gordon equation in AdS, which is basically a linear perturbation around AdS, and then looking at the instability. And there is no reason to believe that you can apply the same criteria in interacting theory. So yeah, the question mark for interacting theory. So this is purely a linear analysis, and then the instability comes from the linear analysis. And so therefore, I think from the Bootstrap or a more non-perturbative point of view, it's a bit unclear whether this scenario is really relevant, because anyway, we expect that this transition to happen at some interacting point. So yes, so because I don't believe in this scenario, so it's probably fine that this picture is small. Exactly, that's what I'm going to talk about. That's what I'm going to talk about in the next lecture.
More questions? There's one there.
Question is a bit orthogonal to the stuff you were talking about so far, but since your construction very explicitly has an IR regulator, you know whether this formalism helps you address issues people have been having with defining IR finite S matrices, when you have massless QED and so on, there's this issue of memory and getting kicked out of Fock spaces and so on.
Yeah, I think it's an interesting question. But at this point, I don't have much to say about it. Well, certainly, things are completely IR finite as long as the AdS radius is finite. Then the question is whether you can define some natural IR finite observable by taking the flat space limit. And then I think that's an interesting question. There are some discussion in the context of scalar QED by Lorenzo and Anko, but nothing is explored systematically.
All right, any more questions? Yes.
Yeah, I just wanted to address a point about Neumann. I mean, the way why we say there is Thanks. Okay, the reason we say there is a gauge theory on the boundary is just that we take, the gauge transformations of the boundary, reduce to gauge transformation for the small a, and then you can build a spectrum of this putative CFT by taking, the usual procedure of building it out from F and looking at partition function and so on, and imposing the single constraint. So that's why we say there is a gauge theory in this sense. I hope this kind of clarifies this point.
I guess he was answering to Joao.
Any more questions? No? Let me say that I have this watch and it counts how many steps I take, so I would really appreciate questions from the back rows as well in future talks. We'll take a break. Let's resume 12:15. All right, thanks, Shota, again.